are finally moving on beyond atoms. We now begin to put atoms together and form compounds. Now, we're not concerned about the processes that govern the chemistry that make the compounds at this stage, just the compounds themselves. Now, we can't ignore chemical reactions completely in our discussion of the compounds, but remember, we are focusing on the different types of matter that form from the elements, not how they form at this point.
In this first lecture on compounds, we're going to concentrate on the composition of the compounds regarding the elements, but we need first to define and categorize some of our chemical terms. Let's review the definition of a compound. A compound is a substance when two or more elements bond. So how did scientists figure out what elements were in the different compounds? Well, four concepts made life easier in determining the elemental makeup of compounds. 1. All samples of a compound, no matter where found or made, will have the same proportions of the elements. This discovery, stated by a French actor and chemist, Joseph Proust, in 1799, is known as the law of constant composition or law of definite proportions. Now, if you were to make a compound artificially in a lab and then find that same compound in nature, the percentage by weight of the elements in your synthesized compound and the natural one will be identical. Now, you might ask if there are exceptions to this rule, and the answer is actually yes. There are exotic compounds called non-stoichiometric compounds that do exist. 2. In Dalton's atomic law, John Dalton stated that atoms tend to combine in small whole number ratios of one another to make up compounds, and we call this law the law of multiple proportions. Again, there are interesting exceptions to this rule, but a bit beyond us at present. Now, 3, we're going to rely on Lavoisier's conservation of mass. The mass is considered to be constant throughout a chemical reaction process, which makes it easier for us to calculate the ratios of the elements in a simple synthesis reaction. In these reactions, we envision pure elements coming together to make compounds. Such a reaction would be hydrogen and oxygen gas combining to make water. Now, we've also seen decomposition reactions, such as the electrolysis of water into hydrogen and oxygen gas, where we tear apart compounds, getting back the elements. And finally, we have a good sense of the relative masses of the atoms, and it's an easy matter to weigh things and get the mass of compounds and elements, or, by using Avogadro's number, count the number of compound molecules or elemental atoms. And we can freely convert back and forth between masses and number of particles and moles. Experimentally, there are 3 primary methods to get at the ratio of the different elements in a compound. We can take a known amount of a compound, tear it apart to its basic elements, and measure the mass percentages of each element that was in the compound. As stated before, we call this a decomposition process. Now, for simple compounds, we can mass the elements before a synthesis reaction, react them to make a compound, and then measure the mass of the final compound and any of the elements left over. Once we know all the masses, it's a rather straightforward process to compute the relative mass percentage of the elements contained in the compounds. Now, in this modern era, we have a variety of analytical tools and instruments that can help us determine the elemental makeup of a compound, as well as the molecular mass of the compound. Once we have this data, it's a rather straightforward computation to get at what we call the chemical formula. So let's define what we mean when we say chemical formula. The typical chemical formula consists of atom types and subscripts that represent the relative number of each atom type in the chemical compound. For example, the chemical formula for the compound ammonia is shown. For a single particle of this compound, there are 3 atoms of hydrogen denoted by the subscript 3 and 1 atom of nitrogen. Notice, instead of showing the number 1 as a subscript for nitrogen, it's implied. These numbers are considered constant and do not change if the compound is ammonia. The law of constant composition binds us. Now, chemical formula come in three general types. An empirical formula is a chemical formula that represents the simplest, most reduced ratio of the elements in a single molecule of the compound. A molecular formula is a chemical formula that represents the actual number of atoms and type of elements in a single molecule of the compound. The molecular formula can be reduced to an empirical formula by an integer divisor. For example, if we look at the compound butane, it has the molecular formula of C4H10, which means that there are 4 carbon and 10 hydrogen atoms in one molecule of this compound. But this is not the most reduced form of the formula. We can divide the numbers by a common integer multiple, 2. C2H5 is the empirical formula and gives the simplest ratio of the atoms, 2 carbons for every 5 hydrogens. We see, too, that the empirical formula gives us the correct ratio of atoms, but not the best description of the actual compound itself. But we can be assured that the empirical formula will always be a whole integer multiple of the molecular formula. In this case, multiplying the empirical formula by 2 gives us the molecular formula. Look carefully at how this is written on the slide. Now, chemical formula give us a relationship that links the number of different elements that make up this compound to one particle of the compound. Now, what if we had 1 mole of the C4H10 compound? How many total moles of carbon and hydrogen atoms would we have? Well, counting atoms or counting moles of atoms doesn't matter. We obey the same ratios. For example, I know that if I had 1 molecule of butane, C4H10, the molecular formula tells me that I have 4 carbon atoms and 10 hydrogen ones. In the same way, 1 mole of C4H10 molecules must have 4 moles of carbon atoms and 10 moles of hydrogen atoms. We will use these kinds of relationships often in chemical computations. There is one last formula to be aware of called the structural formula. This structural formula is a picture of the actual arrangement of the atoms in the compound and can be drawn in several ways with varying levels of detail. For example, let's look at the structural formula for ammonia. Now, first, we notice that the empirical formula and the molecular formula are one and the same in this example. Now, the main drawback for molecular formula is that it gives us little detail about the actual arrangement of the atoms within the molecule. For all we know, the arrangement could be an NHHH. So, what is the correct structure for this compound? A guiding principle is in simple molecular systems like ammonia is to arrange the atoms in the most symmetrical way possible. This guess of the skeletal structure is a good first approximation. Here are some of the ways that we might represent this molecule. The first 2 are what we call Lewis representations. We'll be learning how to generate these types of structures very soon in the next few lectures. The first structure pictures the bonding between the N and H atoms in the molecule with a pair of dots representing electrons. There is also a lone pair of electrons hanging on the nitrogen atom. The second representation simply replaces the bonding pair of electrons with a straight line. Both of these representations are crude structural pictures. The third representation gives us more detail as to the 3-dimensional arrangement of the atoms. The dark lines represent bonding between atoms coming at us off the plane of the screen, and dashed lines represent atomic bonding going into the plane of the slide. We see a kind of pyramidal arrangement of the atoms with the lone electron pair sitting on the top of the nitrogen. Looking at just the atoms, we would say that this molecule has a trigonal pyramidal shape. Now, in this age of computers, it's also common to see something like the fourth structure representation, a very nice 3D picture in which we can be very specific about the distance between the atoms and actual bond angles.
In the next few lectures of this series, we'll be learning some simple methods to estimate the structure of the molecules that form compounds. Now, as you progress in the study of chemistry, you'll learn about sophisticated analytical methods and high-level quantum mechanical computations that chemists rely on to characterize the composition and structure of very complex compounds, with amazing accuracy and precision too. Really fun stuff. But as with everything, we have to first learn how to walk and then run before we fly. Stick with it. Catch you later.